Okay, to start. Okay. Welcome everyone to Harvard CMSA Quantum Matter in Math Physics seminar. We are happy to have Tat Lam from MIT. We will actually meet up with Hotat in the afternoon at Harvard area, maybe at the CMSA or physics department. And if you have interest to join us, email me. And today he will be speaking about topics of his recent work on non-invertible symmetry involves gaplessness. Let me remind the audience, please feel free to ask questions and interact with Hotat during his talk. And let's welcome Hotat. Please, Hotat, thank you.
Thank you. So first of all, I'd like to thank everyone for coming. Yeah, I see that also there are some people at the West Coast, so it's probably very hard for them to wake up. Today I'll be telling you something about non-invariable symmetry enforced gaplessness. And this is mostly based on this work that I've done in collaborations with Anuj and Clay, both from U Chicago. And so I'll also discuss some results that were reported in these two papers with Iter, Clay, Hoshen, and also Shuhan. Okay, so let me begin with some general introductions. Suppose we are given theory in the UV. So this UV theory can be defined by some lattice models, or it can be defined by some continuum field theories. So often we want to ask what happens to these theories in the infrared. So in general, this is a very hard question because most of the times the theory becomes strongly coupled in the infrared. And there are also many different possibilities that could happen in the infrared. So in this case, symmetry becomes a very useful tool to deduce some rigorous results about the infrared dynamics. And also it helps us to organize various possibilities in the infrared. So suppose we start with a UV theory with some global symmetry G. So there are, broadly speaking, two possibilities. So we can just classify that, group them into two categories, depends on whether the symmetry is spontaneously broken or not. So if the symmetry is spontaneously broken, then the theory will flow to a spontaneous symmetry breaking phase. And if the symmetry is preserved, then we can invoke more criteria to refine the classifications of different possibilities. So one criteria that we will use in this talk is that we will divide the phases further, depends on whether there's a gap in the spectrum. So if there's no gap in the spectrums, then the theory will flow to a symmetry-preserving gapless phase. And most likely it will be a CFTs. Sometimes it can be some other theories with, for example, Lifshitz theories and things like that. So in the other categories, which is symmetry-preserving gap phases, we can further divide it into two classes. So one class is the one that, in a colloquial sense, what people usually refer to as a trivially gap phase. And in more formal sense, I will call it invertible phase. So what I mean by invertible phase is a phase where its partition functions, when you compute on any manifolds, it's always a phase. Its modulus is always 1. And in particular, if we place this theories on some spatial topology, then we'll find that it always have a unique ground state. So independent of which topology the spatial manifold is. So in condensed matter language, because this symmetry G is preserved along the RG flow, so one can also think of this invertible phase as a symmetry-protected topological phase protected by the symmetry G. Okay, so other than this symmetry-preserving invertible phase, there are also some non-trivial symmetry-preserving gap phase. These are what I will call symmetry-preserving topological orders. So what I mean by symmetry-preserving topological orders is just some non-trivial topological quantum field theories that live in the IR. So a non-trivial topological quantum field theory, a defining characteristic of them is that if we place it on some spatial manifolds, it will have some ground state degeneracies, and the ground state degeneracy will depend on the topology of that. Okay, so let me summarize. So in general, there are 4 possibilities that can happen in infrared. So one is a symmetry breaking phase, the other is a symmetry preserving gapless phase, and the third one is symmetry preserving invertible phase, and the fourth one is symmetry preserving topological order. Okay, so there are all these possibilities. But one question that we would like to ask is what happens to the theories? What does it flow to? Which phase it flow to? So in general, there's no obstructions that one can derive to obstruct a symmetry preserving, a symmetry breaking phase. But in some cases, we can say something about symmetry-preserving phase. So for symmetry-preserving phase, a useful tool for it turns out to be the topology of the symmetry. So suppose we know that the UV theory, the global symmetry G has a non-trivial topology. Then immediately we can say that the theory can never flow to a symmetry-preserving invertible phase. So the reason is because a topology is preserved along a renormalization group flow, and the invertible phase always have trivial anomalies. So there's no way for invertible phase to reproduce the topology or match the topology of the UV theory. So this gives us a no-go theorem, and this kind of theorem is very much similar to, in spirit, to the LSM theorems that has been discussed in this matter literature. And in some cases, anomaly can be more interesting. So sometimes the anomaly can be extremely strong. It can be strong enough to even exclude all possible symmetry-preserving gap phase. In particular, it can exclude even the symmetry-preserving topological order. And this phenomenon is known as symmetry-enforced gaplessness in the literature. And let me clarify the terminology. So when I say symmetry-enforced gaplessness, I mean that the theory always flow to a symmetry-preserving gapless phase. What I mean is that if the symmetry is preserved, the theory will flow to a gapless phase. So in particular, there's no obstructions for the theory to flow to a symmetry-breaking phase. Okay, so this is what I mean by symmetry-enforced gaplessness. So there are various examples of symmetry-enforced gaplessness. So the simplest examples one can think about is the perturbative anomaly of a continuous symmetry. So when I talk about perturbative anomalies, what I mean is that, for example, I can have an anomaly of a chiral fermion, and that is a perturbative anomaly. And it's actually very easy to show that if such perturbative anomaly exists, then the current correlation functions has to decay as a power law. So because of this power law decay, the theory has to have some gapless degrees of freedoms, and that's why the theory always flows to a gapless phase if the symmetry is preserved. So, a more interesting type of symmetry-enforced gaplessness will come from discrete symmetry. So one such example is, for example, in 3+1 dimension, we can consider a mixed anomaly between a ZN symmetry and gravity. And in some cases, this mixed anomaly can also enforce gaplessness if the symmetry is preserved. And another example that people might be familiar with is an example that come up from this nice paper by Gallardo, Kapustin, Komogowski, and Seiberg. And this is a mixed anomaly between time-reversal symmetry and center one from symmetry in 3+1 de Young-Mills theory at theta equals to pi. So it was proven in this nice paper by Clay and Contaro that this mixed anomaly in some case can obstruct symmetry-preserving gap phase. And there are many more other examples that I want to mention here. So in general, oh, sorry, go ahead.
Yes, Hotat, can you remind me, just make sure we're on the same page, which mixed ZN gravitational anomaly symmetry enforced the gaplessness?
Yes, so this is, so you can, for example, imagine that you have a chiral fermion. So the chiral fermion will have a ZN symmetry, right? And the ZN symmetry, in general, it has a U1 symmetry, but let's just talk about the ZN subgroup. So the ZN subgroup can have mixed anomaly with a gravity, and that's a mixed anomaly that I'm talking about. Does that answer the question?
Yes, but like how precisely is that the ZN relation to maybe Fermat parity? Like I think there are certainly other certain mixed ZN gravitational anomaly does not enforce the gaplessness. In the sense, you can also have a symmetric TQFT, right? So I'm just trying to maybe a few sentences clarify which type of a ZN gravitational anomaly enforces gaplessness.
Oh, it's the one that I mentioned, and that the one that I mentioned, let's say it's a single chiral fermion, then this will define a generator of the anomalies. And then I think you need the generators to raise to certain powers. Then you.
Okay. Yeah. The generator, yes. Okay.
Yeah.
Wait, is that
the generators will already do the job? Yeah, that's right. And also, I think some power of the generator also do.
Yeah, maybe, yeah. Yeah, I know that. Yeah, no problem. Thanks.
So, so I mentioned a few examples about symmetry-enforced gaplessness, and in general, there are various different approaches towards symmetry-enforced gaplessness. So, one approach is probably the most ambitious approach one can think of is, why don't we just classify all possible topological orders? and then we understand how to couple them to background gauge fields, and then we compute all the 12 anomalies. And if we can do all these things, then we can have a huge list of tables of all possible anomalies that can be realized by symmetry enriched topological orders. And then we can just check whether the anomalies exist in this table or not. If it doesn't exist in the table, then we have a symmetry-enforced gaplessness. So in general, this is a very hard approach because it requires us to have a complete classifications of topological orders and also complete classifications of symmetry-enriched topological orders and also compute their anomaly. So in some steps towards this direction has been taken in 3+1 dimension in this paper by Ryan Thorngren. And this is because in 3+1D, there was a sort of a proposed classifications of topological orders. It's not 100% sure that this is the complete classification at this moment, but with that, and then with a complete understanding of symmetry enrichments, then one might be able to derive some kind of symmetry-enforced gaplessness in this case. So at least what one can do is that we can construct a large class of topological orders, and then we can convince ourselves that this topological orders doesn't realize the anomalies, for example. So this is one approach. It's a very hard approach. So there's a second approach, which is complementary to symmetry-enforced gaplessness. So instead of showing symmetry-enforced gaplessness, let's just construct explicit symmetry-preserving topological orders and to match the anomaly. If we can construct this, then immediately we know that this anomaly cannot enforce gaplessness. So it turns out that for a large class of anomalies, there's a rather systematic constructions of topological orders that matches the anomaly. And the idea behind this is using the idea of symmetry extensions. And there has been a long list of literatures or long list of papers that study this. So this approach is also very useful, even though it doesn't prove symmetry-enforced gaplessness, but it gives us some hint that some anomaly might potentially give us symmetry-enforced gaplessness. So, and one comment is that in these constructions, typically you will be able to construct some topological orders that saturates the anomaly. But then there's one additional things one need to check is whether this topological order preserves the symmetry or not. So there's a chance that the topological order might spontaneously break the symmetry. Okay, so this is the second approach. So this is complementary to symmetry-enforced gaplessness. So the third approach is really the approach that I will be taking in today's talk. So this is to formulate some abstractions to symmetry-preserving gap bases. So there has been several papers that discuss explicit examples of anomalies, and they show that for those specific anomalies that there's no symmetry-preserving gap bases. And in fact, the word symmetry-enforced gaplessness was first coined in this paper, if I'm correct. So this is the third approach, and in general, one can do it for like one anomaly or anomaly one by one, but it would be nice if there's a general abstractions. And in fact, there's a general abstraction that was formulated in this nice paper. And what they show is that if you evaluate the anomaly on certain mapping torus, if it is non-trivial, then it tells you that your anomaly gives you a symmetry-enforced gaplessness. Okay, so this is in general 3 approaches towards symmetry-enforced gaplessness, and then some of the status in the literature. So in today's talk, what I'm going to do is that I'm going to discuss symmetry-enforced gaplessness using a different type of symmetry. So this is a new type of symmetries known as non-invertible symmetries. And so I'm going to discuss this non-invertible symmetries and argue that this non-invertible symmetries, just like ordinary symmetries, are invariants under renormalization group. And we can then use them to constrain the infrared dynamics. And in particular, I'm going to show that this non-invertible symmetries often forbid symmetry-preserving gap bases. And this generalizes the phenomena of symmetry-enforced gaplessness to non-invertible symmetries. So it turns out that this non-invertible symmetries exist in many familiar systems, so we don't need to go to some exotic land to search for them. So they exist, for example, already in 1+1D Ising models, which we have a very good control over. They also exist in 3+1D Zen lattice gauge theories and also many other examples. So using this rigorous results of symmetry-enforced gaplessness, we can actually make some claims about what happens to the infrared dynamics of this theories. Okay, so this is basically an overview of today's talk. Maybe I should pause here and see if there's any questions.
Hotat, this is Andrei Nevedomsky. Just a quick clarification. So you did mention the connections to the Lieb-Schultz-Matisse-Ishikawa-Hastings type theorem, right? So where, if you're going to talk about this, I apologize for anticipating. But could you give an example? So let's say you give an example here, 1 + 1D Ising model, right? So if I consider spin chain, does the Lieb-Schultz-Matisse result for half-odd integer chains, can it be phrased in terms of this non-invertible symmetries?
Sorry, you say non-invertible symmetries. So it can be phrased in the language of symmetry-enforced gaplessness. But I'm going to discuss. But it maybe the model. I think the model doesn't have non-invertible symmetry. That's the one that you talk about. So, but Ising model will have non-invertible symmetries, and there will be a symmetry-enforced gaplessness from Ising model from that non-invertible symmetries. But in 1 + 1D, it turns out that symmetry-enforced gaplessness is somewhat trivial. The reason is very simple, because in 1 + 1D, there are no topological orders. So once you exclude a symmetry preserving invertible phase, then you're basically done. So the statement will be more interesting in higher dimensions.
Okay, I follow.
Yes, does that answer the question? So maybe.
Well, so just to clarify, so in 1D, the result you get for 1 + 1D, to what extent does it expand on what is known from Lieb-Schultz-Matisse type theorem, or is it just a different way of obtaining the same result?
Oh, okay, good. So in 1 + 1D, if I'm staying in the realm of invertible symmetries, then this is the same as Lieb-Schultz-Matisse theorems. But if I'm talking about non-invertible symmetries, then this will be new results.
I see. So you're saying there are some examples of 1 + 1D gapless systems which have non-invertible symmetries that you wouldn't have known if you just simply applied Lieb-Schultz-Matisse theorem.
Correct. Yeah, correct. I'm going to discuss an example like this. And the more interesting things is in higher dimensions. And I'm also going to discuss example of that.
Thanks.
Good. Is there any more questions? Okay, so maybe I should move on. Okay, so now let me say I'm going to discuss more details, and let me start with some general words about global symmetries. So in modern days, we now think about global symmetries as a set of topological operators in the theory. So there are topological defects. And for example, we can rephrase U1 global symmetries as a set of topological defects, which is also called symmetry defects. So the idea is very simple. We just take the net occurrence of the U1 global symmetries, then we integrate it over some codimension 1 manifold. So this will define some defect. And this defect has several properties. So first of all, it's codimension 1, which I already mentioned. Second property is that these are topological defects, which is a crucial property. So when I say the defect is topological, what I mean is that if this defect is in some correlation functions, it's fine to deform the underlying manifolds M of these defects without changing the correlation functions, unless this manifold crosses some local operators. So this is a property that these defects are topological. And the third property, which is crucial, is that since these defects are topological, we can talk about their fusions. We can collide them. And when we collide them, this will define a new topological defects. And the way this topological defect fuse is just like how the symmetry multiplication, the group multiplication works in the symmetry group G. Okay, so these are the three characteristics of the topological defects of an ordinary global symmetry. So this perspective of thinking about global symmetry as some topological defects is extremely powerful and useful because they lead to several generalizations of ordinary global symmetry. So one generalization, which is almost a decade old now, is the higher form symmetry. So the idea is to modify the dimensionality of this symmetry defects. So instead of talking about symmetry defects of codimension 1, we can talk about symmetry defect of higher codimensions. So for example, in 2 + 1Ds, we can, instead of talking about symmetry defect like surfaces, we can talk about symmetry defect made of lines. So for example, there can be anions inside them. So somewhat orthogonal directions to these generalizations is to modify the fusion rule of the symmetry defects. And this is known as non-invertible symmetries. And I'm going to discuss examples of non-invertible symmetry and say more about this later. So, and also there are other various generalized symmetries one can discuss. Okay, good. So what are non-invertible symmetries? So non-invertible symmetry arises from recognizing the fact that in general, topological defects in quantum field theories do not fuse as a group. So they can have, they can obey a more general fusions. And one characteristic of this more general fusion is that this topological defect can be non-invertible. So that's why this symmetries are called non-invertible symmetry. So when I say a defect is non-invertible, what it means is, for example, if we take the defect and its orientation reversal, we can fuse them. So if the fusion is a group-like fusions, then this will just give us identity. But if the fusion is not group-like fusions, in general, it will give us something that is not identity plus some additional stuff. So because of this, we call a defect non-invertible. Okay. So one way to think about this in Hamiltonian pictures that might be helpful is that, first of all, these defects, if we think of them in Hamiltonian pictures, we can let them be something that is inserted at a fixed time. Then they will define some operators that act on the Hilbert space. And since these defects are topologicals, then they has to commute with the Hamiltonian. But the property that these defects are non-invertible simply means that this defect is not a unitary operator. So unlike the usual symmetry defects that we defined before, which is a unitary operator. So this is a characteristic of a non-invertible symmetry. And I'm going to discuss example of this type. Okay, so let me say some general words about non-invertible symmetry. So in recent years, there has been a lot of discussions and application that maybe you should think about this non-invertible topological defects as some generalized global symmetry. And of course, the reason, of course, one will ask, well, why should we do that? Why is it fair to think of them as a global symmetry? And there are many good reasons. So one reason is that just like ordinary global symmetry, they lead to selection rules and conservation laws. And the second reason is that in some cases, this just like ordinary global symmetries, this global symmetry can be gauged. And the third reason, which would be closely related to today's talk, is that this non-invertible topological defects are invariants of renormalization group flow. So one way to think about this is the following. So when we do renormalizations, we are sort of like doing a zoom in and zoom out process. But if the operator or the defect is topological, then this will survive at every scales. So because of this, this is invariance of renormalization group flow. And then we can use this fact that this defects or this non-invertible symmetries are invariant under renormalization group flow to deduce some non-trivial constraints on the infrared dynamics. And this will also be the sort of the central theme of today's talk. And I'm going to demonstrate the example of this time. Okay, so let me now discuss concrete examples, which I already mentioned before. So this is Ising CFT. So first of all, in 1+1D, so I will be first focused on 1+1D. So in 1+1D, turns out that non-invertible symmetries or non-invertible topological lines exist in almost everywhere. It exists in almost every rational CFT. So in particular, Ising CFT is a type of rational CFT, and there are non-invertible lines in Ising CFT. So in total, there are 3 topological lines in Ising CFTs. One is the trivial line. The other is the Z2 symmetry line, which I denote by eta. And the other is the duality line. So the Z2 symmetry line is closely related to or it defines or is connected to the Z2 symmetry of the Ising model or the Ising CFT. The more interesting one is the duality line. So the duality line, if we take 2 of them, when we fuse them, we don't get identity. Instead, we get identity plus the Z2 symmetry line. So because of these fusions, we see that there are multiple objects on the right-hand side. We call this duality line non-invertible. So another way to see that this duality line are non-invertible is that we can ask how does it act on local operators. So for example, when it acts on the spin field operator sigma, what it do is that it will map the local spin field operator to a non-local disoperator mu. And this non-local disorder operator is attached to a symmetry line. So that's why this is non-local. And the direct consequence of this is that now if we work in Hamiltonian pictures, then we can ask how does this duality line acts on the Hilbert space. And we see that this duality line actually annihilates the states that due to the or corresponds to the spin field operator. And that's why this duality line is not invertible line. So it's a non-invertible actions on a Hilbert space. Okay, so it turns out that this duality line is closely related to the Kramer-Swanner duality in a Ising model. And so Kramer-Swanner duality says that in Ising models, the low temperature phase and the high temperature phase are related by duality. And in particular, at the self-deal point, which is where the Ising CFT sit at, this becomes a self-duality of the Ising CFT. And the precise statement of this self-duality is that the theory of the Ising CFT is invariant under gauging the Z2 symmetry. So this is a precise statement of Kramer-Swanner duality. And it turns out that the Kramer-Swanner duality it's equivalent to the existence of duality lines. So we can show that if the duality line exists, then the theory must have Kramer-Swanner duality, and vice versa. If there's a Kramer-Swanner duality, there must be a non-invertible duality line in theory. So let me show it in one way first. So let's assume that we have some duality line in the theory. I'm going to show that the theory has a Kramer-Swanner duality. So the way to derive this Kramer-Swanner duality is the following. So let's imagine that we place our CFT on some torus, okay? So then we can imagine that we pop up, we introduce duality lines, small duality lines at some small circle. So this this new partition function is related to the original partition functions by the quantum dimensions of the duality line. Okay, so now we can make this duality line grow and make it larger and larger, and eventually let it wrap around the whole torus. So when we do that, this is what I've drawn on the left-hand side of the equations. So this is what I've drawn here. So now we can make the duality line bigger and bigger. So eventually, this duality lines will be very close to each other, and then we can apply the fusion rules of these duality lines. So if we apply the fusion rule of these duality lines, then we learn that this partition functions is the same as the partition functions with insertions of the Z2 symmetry lines. And in particular, it's a sum over all possible insertions of the Z2 symmetry lines in the torus partition functions. And the physical meaning of this sum is just means that we are gauging, or we are doing the orbifold of the Z2 symmetry. So the upshot is that now we can relate the torus partition functions with the torus partition function after gauging. And in fact, they are the same. And that is the precise statements of Kramer-Swanner duality.
So, Hotat,
Yes.
I'm sorry, maybe could you rephrase it? So let's say if we did it in 1+1D, when you say torus, should I just visualize a spin chain with periodic boundary conditions? And then what you do, if I understood correctly, you create a special region and you extend it through the entire line until it wraps over the entire torus. Then how do I see the fact that it's non-invertible? Like how, could you repeat the argument for this particular case?
Oh, you mean why this duality line is non-invertible on the spin chain?
Correct. Or maybe could you, I guess you lost me in the explanation. I wonder if you could make it explicit for the case of 1+1D.
Oh, okay. Yeah. So in the spin,
I guess Andrew want to hear something more like along the operation on the spin chains, that type of a description.
Well, yeah, or at least let's say less, should I say, less abstract, not in arbitrary dimensions, but in one dimensions. What do you mean by duality line? Right. For instance, why is it called duality line? Is it because codimension 0 relative to a system? Anyway, I'm confused also about the language. But
oh, right. Yeah. So when I say duality line, it's because I'm thinking in Lagrangian formalisms, like in a space-time formulation. So it's a line in space-time, and if we restrict it to a fixed time, then this will be defining an operator at the fixed times that acts on the Hamiltonians. Okay, and then you can ask how do I write down explicit expression of this duality line? So it is somewhat complicated, but the upshot is that when you act this duality lines, what happens is that it does not it's not a unitary operations. It will map a sum of the states to it will annihilate some of the states, and this is expected from the actions on the CFT language that what I've described here, that this duality lines will annihilate a state that is correspond to the spin field operator. So yeah, as for the explicit constructions, I cannot explain it right now, but there are papers that work it out explicitly. Yeah.
Thank you, I appreciate it.
Okay, yeah. Good, yeah, good. So so now so now I discussed that the existence of these duality lines implies Kramers-Wiener dualities. One can ask what happens in the reverse directions. If there's a Kramers-Wiener duality, do we always have a duality line? So the answer is yes. So again, I'm working on space-time formulations. So what happens is that you can imagine that you do a half, you gauge the Z2 symmetry in half of the space-time. So if you do that, you need to impose some boundary conditions on the interface. And the boundary conditions that I'm going to impose is a dirichlet boundary conditions for the Z2 symmetry. And a dirichlet boundary condition for Z2 symmetry is always a topological boundary conditions. And in this case, now I can use the fact that there's a Kramers-Wiener dualities to relate the theories on the left-hand side and the theory with the right-hand side, so we can identify them. So a direct consequence of this is that this interface now becomes actual defects in the theory, in this single theory. And so this means that Kramers-Wiener duality defines some defects, which I'll refer to as a duality line in this theories through half gauging. And in fact, using these descriptions, we can rederive the non-invertible fusion rules of this duality line. So we can imagine taking two duality lines and then to refuse them. So a physical meaning of this fusion is just means that we gauge the Z2 symmetries in the regions that is bounded by these two duality lines. And gauging a Z2 symmetry amounts to inserting various Z2 symmetry defects. And in particular, this Z2 symmetry defects has to be parallel to these two duality lines. So as a result, we learned that if we fuse two duality lines, it's equivalent to the fusion of 1 plus eta. Okay, so this gives us the derivations from Kramers-Wiener duality to duality line. I think there's someone raising hand.
Yeah, Hank, go ahead.
Yeah, I'm just wondering, because the argument here doesn't seem to depend on the fact that you have C2 symmetry. Like I can say a system has like Zn symmetry and then it's like symmetric under gauging the Zn symmetry. Is the same argument going to hold? Or?
Correct, yeah. So precisely, you can replace this Z2 symmetry by Zn symmetry, and then and then you can also define the corresponding duality lines. And the category behind these things is called Tambara-Yamagami categories, which is the Ising category. Yeah.
Okay, cool. Nice.
There's another raise from Andre.
Yeah, sorry. I'll be quick. I don't mean to distract you. But if I were to think of your right-hand side box, right, proving that from the existence of Kramers-Wiener that there's a duality line, would I be correct that in example of a one-dimensional chain, you would argue that when you draw these two parallel lines, that's like saying I do two Kramers-Wiener transformations at different times. So let's say I don't have relativistic Lorentz invariance, and I think of time as just a parameter. So I do it at time t1, and I do another Kramers-Wiener at a later time t2. And you're saying if I now think of fusing the two, the result is not, because they're non-unitary, somehow I could get a linear superposition of going back to initial transformation, or, you know, so how do I think of this fusion, d cross d equals 1 plus eta? What would be the eta in that case?
Oh, the eta will be doing a Z2 symmetry transformations on the Hilbert space. Yeah, but maybe a way to think about this, a simpler way to think about this, like Kramers-Wiener duality line, is to think of them as defects. So first of all, these are lines. So there are two ways to think about them in Hilbert space. One is that we place it at a fixed time. So this becomes an operator. There's another way to think about this is that let's just place it in time directions. So this is what defines the defects in the Hilbert space. So it's actually easier to describe these defects in spin chains. And I don't precisely remember what it does, but what it roughly speaking is to modify to one bound or something like that, the interaction of one bound. then there's a very easy way to check these fusions. Now you can literally just inserting two defects by modifying your Hamiltonians at two bounds, and then you can just fuse them. And you can do some unitary transformations to move this, to transform your Hamiltonians, move this bound, and then eventually fuse them. Then you will see that it will amounts to inserting 1 plus eta in the time directions. So that's an easier way to check it. As for operator, it's a little bit harder.
Gotcha. Thanks.
Okay, so I'll now move on. So now I'm coming to one of the main points of today's talk is that so this duality lines turns out can be used to constrain renormalization group flow. So in particular, this duality line is incompatible with an invertible phase. So this statement is very much similar to a statement of the topology. And let me now argue why this is the case. So the argument is the following. So suppose there's an invertible phase, then this invertible phase has to be also a Z2 SPT. That is because in the UV, there's a Z2 symmetry. So Z2 symmetry persists. So this invertible phase has to be a Z2 SPT. Okay. So Z2 SPT are very well understood in 1+1D. They are classified by the group cohomology. And it turns out that there's only one unique Z2 SPT to talk about, namely the trivial one. Then the next things we need to do is just to check whether this Z2 SPT is invariant under gauging or not. So if we gauge this Z2 SPT, we get a Z2 gauge theory, which describes the spontaneous symmetry breaking phase, which has two vacuum. So that immediately tells us that the Z2 SPT is not the same as Z2 gauge theory. So so this Z2 SPT is not invariant under gauging the Z2 symmetry. So then we conclude that this Z2 SPT does not have the duality symmetry, and it does not respect the duality symmetry. So because of this, there are no self-dual or duality-preserving invertible phase. So this argument tells us that the existence of duality line or the existence of duality symmetry forbids an invertible phase. So this is very much similar to a statement of topology that certain invertible phase are forbid because of the symmetry. And this is also similar to LSM type theorems, except that now we are invoking this duality symmetries, which is a non-invertible symmetry. Okay, so let me make another comment, which was related to questions that was asked before. So in 1+1D, it turns out that the statement of symmetry enforced gaplessness is somewhat trivial, simply because there are no topological orders in 1+1 dimensions. So that means that if we have a topology, then immediately we have symmetry enforced gaplessness in 1+1D. And so in particular, in this case of duality symmetries, we can argue that a theory with duality symmetries must either spontaneously break the symmetry or flow to a gapless CFT. So this is the statement of symmetry enforced gaplessness. And it's also similar to the statements of LSM in 1+1. Juven, you have a question?
The third bullet points in the argument, gauging the Z2 SPT in 1+1D, right?
Yeah.
Gives a 1+1D Z2 gauge theory.
Correct. Yeah.
But that's a 1+1D Z2 topological order, which is not even a topological order.
Yeah, I'm not referring to this to a topological order.
Okay, that's fine. But then what do you say in the next? So it is not under the Z2 gauging? It is not. Just
so then the Z2, so now we check that Z2 SPT after gauging becomes a Z2 gauge theory. So that means that the Z2 SPT cannot be invariant under gauging the Z2 symmetry.
But the Z2 SPT is a trivial class, right? It's a trivial,
trivial class.
Which just means a trivial gap phase.
Correct. Yeah.
But the Z2 gauge theory, as I say in 1+1D, is also not robust, which also trivial phase.
Sorry.
That's trivial as trivial. The theory before and after gauging both are trivial, right?
No. Sorry. Also, I think I missed the words here. So what I mean is it is not invariant under gauging the Z2 symmetry.
But I give an interpretation, it could be invariant. Maybe did you get?
No, the reason is that Z2 gauge theory has two vacuum, right?
Yeah, so, but those vacuum are not robust in 1+1D. You can just use local operator to leave the degeneracy. So that's the statement. There's also no 1+1D topological order for Bolzani system.
Correct, but now I'm staying deep IR. So I'm just want to ask what happens if I gauge the symmetry. Now I'm already in deep IR. I'm not turning on any operator anymore.
Okay.
So one way to think about it is that you start with one vacuum. If you gauge it, you get two vacuum, right? So then there's no way that the theory before and after are the same. So that's why the theory is not invariant under gauging. Does that make sense?
Yeah, theoretically, when you write the partition function for that statement, I agree they are not the same before and after Z2. But I say the phase of themselves, they could also be interpreted as a gap phase. Maybe the second one will have a Z2 symmetry breaking at IR. I guess the total degeneracy for that Z2 gauge theory may be interpreted as the symmetry breaking degeneracy.
Correct. Yeah, correct.
Okay, but anyway, but I think I agree they are not the same, exactly the same after Z2 gauging. Okay.
Right. Yeah.
Right.
Correct. Yeah.
Yeah. Okay. Thanks.
Yeah. Yeah. Is there a question? Or?
Yes.
Oh, hi, Max.
Hi. Good question. Is there an alternative argument why you cannot have an invertible phase?
Alternative argument? What do you have in mind?
I mean, isn't there a statement that if the quantum dimension of the defect is like irrational, then it has to be
correct. Yeah, there's an alternative arguments using the quantum dimensions of the operator. Yeah, but here I'm presenting this one because this one is simpler to explain, and of course this one doesn't generalize to every case. And I'm going to this one is also the statements that I mean this approach is also the one that I'm going to use in higher dimensions. Yeah. I think there's another question from Tibu.
Yeah, hi. So from a StatMag perspective, I would think of the duality as kind of going between the paramagnet and the ferromagnet. So is there not an even stronger statement you can make here that you can even rule out the symmetry breaking phase?
Symmetry
and
breaking.
only end up with gaplessness?
Oh, correct. Yeah. You're right. Yeah, I can also eliminate Z2 symmetry breaking phase. Correct. Yes. Yeah. Does that answer your question? Sorry.
Yeah, I think so. I guess it's not obvious from the argument.
Yeah, it's kind of obvious. Yeah, that's right.
Okay.
It's just different starting points. Yeah. Okay. Is there any more questions? Okay, good. So now I'm moving on now. Now I'm getting to real meat of today's talk. I'm going to discuss what happens in higher dimensions. So what happens in 3+1 dimensions. So the first question one may ask is that are there non-invertible symmetries in higher dimensions? So the answer is yes. And in fact, in today's talk, I'm going to focus on a specific type of non-invertible symmetry in higher dimensions, and they are called duality symmetry. So in particular, I will be working in 3+1 dimensions. So just like how duality symmetry works in 1+1 dimensions, in 3+1 dimensions, if we can find a theory that is invariant under gauging, then we can construct a non-invertible symmetry. So in particular, what we want to consider is a 3+1 theory that is invariant under gauging a ZN1 form symmetry. So if such theory exists, then we can construct a non-invertible duality symmetry by doing half gaugings as before. We gauge the symmetry in half of the spacetimes, we impose dirichlet boundary conditions. This defines a non-invertible duality defects, which is topological. And the existence of this duality defects also implies the symmetry. Implies the invariance under gauging. So one can also explicitly check the fusions of this duality defects with its orientation reversals. So when we fuse them, it is like gauging in thin slab. And this will be translated into sum over all possible insertions of Zn one form symmetry surface on this three-dimensional volumes. And it's probably not hard to convince yourself that this the things on the right-hand side is not identity. So because of this, we call this duality symmetries a non-invertible symmetry. Okay, so it turns out that this duality symmetries exist in many familiar examples. For example, they exist in Zn lattice gauge theories, which is going to be the prime example that I'm going to discuss. And also they exist in Maxwell theories in various Yaml theories like supersymmetric one and non-supersymmetric one. Okay, so the questions that I'm going to answer in today's talk is that we have this nice set of non-invertible symmetries in 3+1 dimensions, can we use them to exclude some phases? So for example, are there duality preserving invariable phase? To answer this, we can do it in a systematic way, as what we did in 1+1 dimensions. And that's why I prefer to explain the abstractions in 1+1 dimensions using invariance under gauging. Okay, so first of all, let's consider a duality preserving invariable phase. So a duality preserving invariable phase necessarily has to be a phase that preserves a Zn1 from symmetry. So it's in other words, it's also a Zn1 from SPT. So Zn1 from SPT are classified, and their partition functions on a spin manifold on any manifold is understood. But in particular, in the talk, I will just restrict to spin manifolds so that the result is easier to state. And so it's just a technicality. But in the paper, we also consider more general manifold. Okay, so in spin manifold, the partition function of a Zn1 from SPT is given by B cup B with the coefficient 2 pi I P over 2n. Okay, so in particular, there are in total a number of different partition functions one can talk about, and they are labeled by an integer P. And this P has a periodicity of n. Okay, so now we have this n possible Zn1 from SPT. We can now ask what happens when we gauge them. So if there are SPTs that are invariant under gaugings, then they preserve the duality symmetry. Okay, so when we gauge the Zn1 from SPT, this is what we get. So we sum over all the Zn two-form gauge fields. So we promote big B to little b, which is a dynamical gauge fields. We also couple little b to a background gauge field big B. So this is the coupling to background gauge fields. Okay, so this is the partition function after gauging. So let's try to understand what we get after gauging. So a quick way to see what the
quick question.
Mm-hmm.
So is the reason that you have the second term such that when you integrate out little b, you regain the first partition function?
Correct. Yeah, correct. So one way to think about this coupling is you can think of so after gauging you have a dual Zn symmetry, and the dual Zn symmetry is generated by the Wilson surface of little b, and this coupling just tells you that I'm coupling the background gauge fields to that dual Zn Wilson symmetry.
Okay, thank you.
Okay, good. So now let's try to understand what this gauge theory is. So we can look at the equation of motions. So equation of motion tells us that P times little b is related to big B mod n. Okay, so let's imagine that we first turn off the background gauge fields. Then we learn that P times little b equals to 0 mod n. And in general, these equations can have multiple solutions. And the number of solutions is given by GCD P comma n. So this means that this different solutions will give you different, you can think of it as give you different number of ground states. Give you different ground states. So this tells us that the theories after gauging is essentially gauge theories and it's a GCD P comma n gauge theory. Okay, so in general, these theories have multiple ground states, and the number of ground states is related to GCD P comma n. Okay, so now I'm going to use the fact that this SPT is invariant under gauging, so it's a self-dual SPT. So since this is a self-dual SPT, then after gauging, we also want the theory to be an SPT, which always have a unique ground states on any spatial topology. And this tells us that this can happen only if P is coprime to N. Okay, so this is the first constraint that we get for this self-dual Zn SPT. Self-dual Zn1 from SPT. Okay, now for P and N that are coprime, we can evaluate the partition function explicitly. So we can first a complete square, and then we will get a speed up phase factor. This is proportional to B cup B, and with a coefficient minus P inverse. So recall that P and N are coprime, so I can always define an inverse of P in the Zn ring. Okay, good. So this is the partition functions. But remember that other than this phase, there's also a sum or path integral that I need to do. And the sum is essentially a Gauss sum on this spin manifold ends. So it turns out that this Gauss sums always only depends on the signature of the manifold. And it always takes the following form. So it's always an eighth root of unity multiplying the signature of the manifold. So a physical meaning of this Gauss sum or this factor is that if this Gauss sum is non-trivial, then the partition function after gauging can potentially be different from the partition function before gauging by an overall phase. And that phase depends on the signature. And so one can interpret this as a potential gravitational anomalies of this duality symmetry. So it turns out that there's a nice fact that if we work in spin manifolds, then the signature of the spin manifold is always a multiple of 16. So since this is eighth root of unity to a power of 16, then it's always always trivial. So it's always 1. So this tells us that the potential gravitational anomaly actually does not exist in the theory. So this is very good because we always intuitively expect that if there's a SPT that preserves duality symmetries, it should always trivialize the anomaly. It should always have a trivial mix of duality and gravitational anomaly. Okay, now with this partition functions, now we can compare it with the original partition we started with. So if the theory is invariant under gaugings, then the two partition functions should agree. And the two partition functions agree if and only if P and is the same as minus P inverse mod N. And remember that P and N are co-prime, so we can multiply P on both sides. Then we get the conditions that the theory is self-dual if and only if P squared equals to -1 mod N. So in other words, it means that the theory is self-dual if and only if -1 is a quadratic residue of N. And it turns out that these equations cannot always be solved. It can be solved if and only if the prime factorizations of N obey certain properties. So one property it has to obey is that the factor of 2 within an N can at most be 1. So in particular, it means that N is either an odd number or or N over 2 is an odd number. So the second constraint is that all the odd primes of N has to be 1 mod 4. So with these two conditions, then this equations always exists a solution. Okay, so now we derive constraints for the existence of self-dual SPT. So so this is the constraint, and then now we can ask. So the option is that only for this N, then self-dual invertible phase exists. For N's that doesn't take these forms, then self-dual SPT cannot exist. So now let me highlight some of the N's that can have non-trivial can have self-dual SPT. So these are the N that obey these conditions. So they are highlighted here. So we see that the minimal N that can have a self-dual invertible phase is when N equals to 2. Okay. So and the minimal N that does not have self-dual invertible phase is when N equals to 3. And there are also various other N's that you can see from the table. Okay, so now we derive some conditions for the existence of duality preserving invertible phase. I think there's a questions or
question.
Oh yeah.
On a non-spin manifold, is the condition stronger?
Yeah, it's stronger. Correct. Yeah. So this is what I alluded to in the footnote. So in the talk, I'm only restricted to spin manifold. If we consider bosonic TQFTs, then we get stronger result. So for example, bosonic TQFT exclude 2 too. So the condition is that essentially the N cannot have any must always be odd. So, and then all of the prime factor has to be 1 mod 4. So we get a stronger result.
But it's not empty, right? There are still self-dual SPTs even for bosonic.
Sorry, can you say again?
It's not empty. There are self-dual SPTs even for bosonic. Okay.
Correct. Like for example, when N equals to 5, there are self-dual bosonic invertible phase. Yeah.
I see. Thank you.
Yeah. Okay. Good. Is there any other questions? Okay, good. Then I'll move on. So yeah, now let me say a little bit more about this duality preserving SPT. Okay, so let's analyze what happens to a duality defects. So before doing that, there's a surprising fact that one might notice. if people are familiar with like time reversal symmetry in 2+1D TQFTs. So it was pointed out in this nice paper by Mastro and Gomez that if we consider a minimal abelian TQFT A in comma P, then the conditions for this series to have time reversal symmetries is precisely the same conditions that I stated before, that the P squared has to be equals to -1 mod n. So we see that the same condition occurs for self-dual SPT and also occurs in the time reversal symmetry of a minimal abelian TQFT. So it turns out this is not a coincidence. And before that, let me define what I mean by minimal abelian TQFT. So a minimal abelian TQFT is defined for every coprime P and N. In particular, I will consider a spin TQFT. So this is the only conditions that one need to obey. So a minimal abelian spin TQFT, AN comma P, in total have a number of anyons or a number of lines, a modular the transparent fermion lines. And this n anyon lines are generated by an anyon of spin P over 2n, okay? So it turns out that this n anyon lines, together with the transparent fermion lines, they themselves form a well-defined TQFT if P and N are coprime. So this is what I refer to as a minimal abelian TQFTs. Okay, good. So the fact that this same conditions exist for the time reversal symmetry of a minimal abelian TQFTs and self-dual SPT is not a coincidence. And this follows from the fact that that the duality defects of the self-dual SPT actually supports a minimal abelian TQFTs. So let me say a little bit more about this. So if we have a self-dual SPTs, then we can imagine inserting this duality defect somewhere. So since the bulk are completely trivial, then the defect should have a well-defined 2+1D topological quantum field theory descriptions. And this TQFT turns out to be the minimal abelian. So this gives us some potential connections to the two effects. Okay, so let me say also a little bit more about what happens when we insert symmetry defects, the ZN symmetry defects on the left-hand side and the right-hand side. So if we insert a ZN symmetry defects, this can end on the duality defects. And when it ends, it will end on some lines. So for example, from the left-hand side, it will end on the anyon, the generating anyon A of the minimal abelian TQFT. And on the right-hand side, it will end on a different generators, which is given by A to the power P. Okay, so from the left-hand side and the right-hand side, they end on different type of anyons. So the generators of the symmetry surface ends on different type of anyons. Okay, and this will be a crucial fact in the next slides. Okay, so now I'm going to argue that there's actually secretly a time reversal symmetry on the duality defects. So how does it work? So let's first imagine that we insert a symmetry defect somewhere. So that means that we're doing half gauging in half of the spacetime. So I also introduced an arrow to denote the orientation of this defect. Okay, good. So now we can first do a 180 rotations to exchange the left and right. So then we exchange left and right, we also change the orientations on the defect. So if we continue, so this is 180 rotations in Euclidean signatures. If we continue analytically continue to Lorentzian signatures, this 180-degree rotations becomes CRT. Okay, so which is always a symmetry of quantum field theory. Good. So we don't exactly get back to original theory, original systems. But then the next things we can do is that we can imagine gauging the ZN one-form symmetry everywhere. So when we gauge the ZN one-form symmetry everywhere, on the right-hand side, we get the gauge theories. And on the left-hand side, what happens is that we first gauge the ZN one-form symmetry, then we get a dual ZN one-form symmetry, then we gauge the dual ZN one-form symmetry, and we recover the original theory. So upshot is that we recover the original systems, except that the orientations on the defects is swapped. So this becomes a time reversal symmetry on the defect. And now we see that this time reversal symmetry is precisely a time reversal symmetry that acts on the minimal TQFTs. And how does it act on the minimal TQFTs? We can keep track of how the symmetry defects, the ZN symmetry defect in the bulk, how does the surface end on the lines? So we know that on the left-hand side, it ends on A. On the right-hand side, it ends on A to the power P. So that means that if we do a time reversal transformations, then the actions on the minimal TQFT has to map A to the power B. And in particular, the spin, we can keep track of how the spin changes. The spin will change from P over 2n to P cube over 2n. Okay, so remember that this is a tensor symmetry. So the spin of an anion is odd under the tensor symmetries. So because of this, this is only possible if P squared equals to -1 mod n. So we cover the precise same conditions that we had before for self-dual SPT. So this connects the condition for self-dual SPT to the conditions for tensor symmetries in a minimal abelian. Okay, so is there any question at this moment?
Sorry, I have
so-
a question.
Okay.
Sorry, this condition at P squared is equal to 1 to -1 mod n. Take, for example, n to be a prime number just for simplicity. So this is precisely the same condition such that there exists a topological manipulation, namely gauging the one from symmetry, stacking with SPT phases and so on, which brings you to a theory in which the duality defect becomes invertible with a mixed Hotat anomaly with the one from symmetry. Is there any connection between these two facts?
Oh, I see. Good. Let me see. That's something I'm not sure. Yeah. That's something I don't have a precise. Yeah. That's a good point. I don't have anything intelligent to say at this moment. Yeah. Okay. But I agree with you. There's a coincidence here too, and there should be an explanation.
Because, for example, also there is a different condition also for triality defects.
Correct. Yeah, it's the same.
Which, however, I don't see how to obtain from condition of self-duality of SPT phases because it's a bit more strange.
Oh, I think they're also the same conditions, if I remember correctly.
No, it's something like I don't remember it, P squared plus P plus 1 or -1, something like this. But okay.
That's right. So it's a condition different from this one, but I think the conditions for the triality defects to be coming from invertible symmetry is also the same conditions that there's a self-dual self-dual SPT that respect triality.
This is precisely my confusion that you had. Yeah. Okay. So the algebraic condition seems to be different in that case.
Right. Yeah, that's right. Yeah.
Okay.
Yeah. That's a good question. So, yeah, we can talk more about it.
Okay. Thank you.
Okay. Good. So let me move on. So now we discussed duality preserving invariable phase, and the next question I want to ask is that can we exclude duality preserving topological orders? If we can do that, then we succeed in proving asymmetry enforced gaplessness. Okay. So it turns out that there in fact can exist non-trivial TQFTs that are invariant under a Z engagings. So there are self-dual SPT in another word. So let's do a simple example. Let's take n to be k squared. Then a ZK two-form gauge series, or equivalently a ZK gauge theory in 3+1 dimension is self-dual, in the sense that it is invariant under gauging a ZN one-form symmetry. Okay, so let's check it explicitly. So a partition function of a ZK two-form gauge theory is given by a sum over ZK two-form gauge fields, and we can also couple this to background gauge field big B. Okay, so this is the partition functions. If we gauge it, this is what we get. We promote big B to a little b, and then we sum over all possible Zn background with Zn two-form gauge fields, and then we also couple little b to big B. So on the right-hand side, it looks like a completely different partition functions, but then in fact, these two partition functions are equivalent. So the reason is that we can integrate our little c. So if we integrate our little c, what we learn is that little b has to be integer multiple of k. And in particular, it means that little b now is restricted from a Zn gauge fields to Zk gauge fields, and then we recover the partition function on the left-hand side. So the upshot is that if n equals to k squared, there are indeed non-trivial TQFTs that are invariant under gauging. Okay, so now using this like nice little idea, we can now imagine that we take a ZK gauge theories and we stack some ZN1 SPT on top of it. And then we will define some SET, some non-trivial SCT. And then in fact, we can use it to construct duality preserving SCT. And such duality preserving SCT exists only if n takes the following form, that n can be written as k squared times L. And also there's non-trivial solutions to these conditions that already appeared before, that p squared equals to -1 mod L. So if such condition can be solved, then we just stack a Zn1 from SPT labeled by P with ZK gauge theory to get a self-dual TQFT. Okay, so this is an explicit constructions that works for all possible ends given by this. So let me also make one comment that already mentioned before. That is, in general, the partition function before and after gauging can be off by a gravitational counterturn, and this can be interpreted as a mixed anomaly between a duality and gravity. But it turns out that for this self-dual spin TQFTs, that this anomalies are always absent on every spin manifold. Okay, so this is the fact that we learned from explicit constructions. And so this is like the second approach that I mentioned about symmetry-preserving about symmetry enforced gaplessness. That is we construct explicit example of TQFT that preserves the symmetry. But of course, now we would like to prove the converse is also true. That I'm going to prove that in fact duality preserving TQFT do not exist unless this conditions is satisfied. And furthermore, I'm going to prove another property about this TQFT is that if such TQFT exists, it must have trivial mixed duality gravitational anomaly. So this statement is slightly more surprising because this is not expected from in general, a TQFT can still carry non-trivial anomaly.
Makes sense question.
Yes.
Well, if you go back one slide, sorry.
Yes.
So the first equation here, B is a background Zn gauge field.
Correct. Yeah. B is a background Zn two-form gauge field.
So I didn't quite understand this step of stacking with a one-form SPT. Why did you need to do that?
Oh yeah. So I want to construct more. I want to construct more self-dual TQFTs.
Oh, I see. So L equal 1, you go back to the situation. You go back to your first point, but then you
That's
can
right.
construct a bigger family.
Correct. Yes.
But L equal 1 still works. I mean, that's an example of a self-dual.
Correct. Yeah. Exactly. When L equals to 1, L equals 1 always works, right? So then we always get a self-dual TQFT, but it only works when n is like k squared, and then we want to do it for more general n. Yes.
Got it. Thank
you. So now let's move on. Okay. So so now I'm really getting to the part of it's also some other technical part of today's talk. That is, I want to prove these statements, and I'm not going to give you all the details. I'm just sort of sketch how that idea works. But to prove these statements, I'm going to use two properties of the TQFT. So one property is that it turns out that 3 plus 1D TQFT always have non-trivial partition functions on every simply connected smooth spin full manifold. So this includes, for example, S2 times S2, which is going to be the manifolds that I'm going to discuss most of the in the proof. Okay, so this is one property, and the second property is that a surface operator in a 3 plus 1D TQFT that link trivially with all the line operators amid the topological boundary conditions. So this statement is a non-trivial statement, but the converse of this statement is actually a trivial statement. So if a surface operator have a non-trivial topological boundary conditions, then you can imagine something like this. So suppose we are in 3 plus 1 dimensions, then a surface operator can link with a line, okay? But then we can open up the surface operator using the topological boundary conditions, and then we can shrink it. So by doing this, we can always unlink a symmetry operator, a surface with a line. So because of this, we learned that surface operator that have topological boundary conditions must link trivially with all the line operators. So this is a trivial statement, but the converse statement is harder, that a surface operator that link trivially with all line operators also omit the topological boundary conditions. So these are the two. Go ahead.
I just clarify this statement here. You are explaining here, say the 2D surface operator admits, let's see, 1D gap boundary conditions or 1D.
Right, yeah, 1D gap boundary condition.
Okay, no problem.
And so these are the two properties that I'm going to use. And in fact, they can be even proven from a more basic properties of 3+1D TQFTs. So I'm happy to explain more about this after the talk, but in view of time, I wouldn't be able to explain this here. Okay, so these are the two properties I'm going to use. Let's move on. So now let's consider a duality preserving TQFTs. And I want to assume whether this bosonic TQFT or a spin TQFT. So it's just some TQFT that I'm going to talk about. And okay, so now one thing is that let's first consider placing this theories on S3, on a spatial manifold S3. Okay, so we'll refer to, so in general, there can be multiple ground states on S3, and we will refer to this ground states as the local vacuum of this series. So the physical meaning of this local vacuum is that each local vacuum will correspond to topological local operator in the theory. So it's like a symmetry is spontaneously broken. There's some zero-form symmetry that is spontaneously broken. And in general, each local vacuum can also support its own TQFTs. So for example, something that can happen is that the TQFT can have two local vacuum. One is a trivial vacuum, or the other is a vacuum that has a, let's say, Z-engaged theories on top of that. Okay. So now I'm going to argue that because the TQFT is invariant or preserve the duality symmetries, then the duality symmetry has to map a local vacuum back to a local vacuum. So that means that each local vacuum individually preserves the duality symmetry. So each vacuum is individually self-dual. Okay, so this is a very helpful statement, because then without loss of generality, then we can restrict to specific TQFTs which have unique vacuum on spatial manifold S3. So for such TQFTs, then the only non-trivial local operator in the theory is just identity operator. Okay, so now we reduce the problems to simpler problems. We just need to consider TQFTs that have identity operator as the only non-trivial local operator. Okay, good. So now let me go to the next proof. Now let's go to the next steps. So I'm going to use make use of the ZN1 symmetry of the self-dual self-dual TQFT. So in general, so the theory has a ZN1 symmetry, but in general, this ZN1 symmetry may not act faithfully on line operator. So this is, for example, the case in like self-dual SPT, because in SPT all the symmetry acts trivially on the states. And also, it's also the example that we discussed before in the ZK gauge theory. Okay, so now let's assume that the unfaithful part of the symmetry is a ZM subgroup of ZM. Okay, so then this tells us that we can split M into K times big M, where K and M are both integer. Okay, so the precise statements of this unfaithful symmetry is that all line operators in the theory do not transform in a nth root of unity under ZN1 symmetry. Rather, they transform as a case root of unity under ZN1 symmetry. Okay, and this is equivalent to statement that the ZM symmetry act unfaithfully. Okay, so now we can do a next step. Let's gauge the ZN1 symmetry and see what we get. So when we gauge the ZN1 symmetry, we get the gauge theories, and the gauge theories will have a dual ZN1 symmetry. The dual ZN1 symmetry is generated by the Wilson surface operator, which is of the dynamical ZN two-form ratio that we use to gauge symmetry. Okay. So the next step is the crucial step. So the next step is that, in fact, some of this Wilson surface can be opened up. And the reason why they can be opened up is recall that if after gauging the symmetries, those lines that are charged under the original ZN1 symmetries will now be not gauge invariant, and they should be attached with some Wilson surface. And recall that the lines that transforms under ZN1 symmetry all transform with case root of unity rather than nth root of unity. So that means that only the operator u to the power n can end topologically on this ZN charge line. So this means that the ZK subgroup of generated by this u to the power n has to act unfaithfully on lines because they emit topological boundary conditions and they can be opened up. Okay, so with all this, then we learned that the dual ZK subgroup or the ZK subgroup of the dual ZN1 from symmetry have to act unfaithfully. And now let's invoke the fact that the theory is invariant under gauging. So because the theory is invariant under gauging, then we know that the actual full complete unfaithful subgroup of the dual symmetry is not just ZK, it has to be Zn, which matches with the unfaithful symmetry in the original theory. And in particular, ZK has to be a subgroup of Zn. So then we learn a following fact that K has to divide big M. And in particular, it means that big M can be written as K squared times L. So now we already see something very similar to the statement that I made before. And the next things we need to do is to derive an actual constraint on little l. Okay, so now we're going to derive constraints on little l. And what we'll do is we will place the theories on S2 times S2. And let me emphasize that because S2 times S2 is a spin manifold, that's why I couldn't distinguish a spin TQFT or a bosonic. Okay, now let's place it on S2 times S2, and then we turn on background gauge for the ZM unfaithful symmetry. So when we turn on the backgrounds for the ZM unfaithful one from symmetry, so we can ask how does the partition functions behave. So turning on the unfaithful backgrounds for the unfaithful ZM one from symmetry, what we learned is that what it's doing is equivalent to inserting some symmetry surface on the S2 times S2. So for example, if there's a non-trivial holonomy on the first S2, then it's equivalent to inserting a symmetry surface on the second S2 and vice versa. Okay, so now I'm really going to use the property of the TQFT now. So because it's the unfaithful symmetry, then there exists some topological boundary conditions for this unfaithful symmetries, and then we can open up the symmetry operators. So when we open up the symmetry operators, this is like what I've drawn here. So when we open up the symmetry operators, we can shrink them. So when we shrink them, so we will now get, we can now shrink it to something completely trivial, because remember that this symmetry defects, they will intersect with each other. What we can do at most is to shrink it to some local operators at the intersection points. And in total, there are A1 times A2 many of intersection points. So this is what we get. And in particular, this A1 times A2, this local operators at A1 times A2 intersection points are identical operators. So this tells us identical local operators. Okay. So now I'm going to use the second plan. Recall that I'm already working in a TQFTs where the only non-trivial local operators are the identical operator. Then we learn that all this local operator that we get at the intersection points must be some C number, because they must be proportional to identity operators, so there must be some C number. So now what we learn is that the partition function must be some number to the power of A1 times A2, because there are in total A1 times A2 many number of non-trivial local operators. Okay, so the next things we do is that we can use the fact that there's a periodicity in AI. If we shift AI by n, then the partition function should be invariant. So with all this, we can finally obtain this result that we can fix the form of the partition functions with the background A1, A2 turn on to be this. So it's proportional to the partition functions without the backgrounds and then with the phase inserted. Okay, so now I'm going to use this result to derive constraints on L. So to do this, I need to keep track. I need to keep track of how symmetry behaves when we do various gauging. And recall that I only have control over the part of Zn part, not the whole Zn part. So then what I want to do is that I want to consider first gauging the Zn part of the one-from symmetry. So if I do that, I get an intermediate theory, which is Q mod Zn. And its symmetry has two parts. So it has a ZK symmetry, which comes from Zn mod Zn. And it has a dual ZM symmetry coming from gauging the ZM symmetry. So second thing is that we can further gauge the ZK symmetry to get the theory Q mod Zn. So when we do that, when we gauge the ZK symmetry, we get the dual symmetry, and then the dual symmetry becomes a ZK subgroup of Zn. I think there's a question.
Yep. So here you're assuming that the Zn splits, right, into Zm times Zk.
No, I didn't assume it's split.
But if it doesn't split, then you get a mixed anomaly between the two sectors, and then you can't gauge Cm by itself, can you? That's an obstruction to gauging Cm.
You're talking about the intermediate theories, right? You're talking about this theory.
Yeah. So the first step. Yeah. So you need to assume that Cn splits, like the central extension that defines Cn as a central extension of Cm has to split, right?
No, I don't need to assume that. So first of all, you're correct that at this step there's a mixed anomaly, but the mixed anomaly doesn't prevent me to gauge a single symmetry, right? So then I can gauge the Zk symmetries. What happens is that the Zm symmetry will have to sort of break. So, but the more precise sentence is that after gauging the Zm symmetry, actually will combine with the dual Zk symmetries into a Zn symmetry.
Yes. Yeah. Okay.
Yeah, in fact, that's a crucial step. Yeah, that's a very crucial step. How all the symmetry behaves as we gauge them, and then this will be important.
Okay, thank you.
Yeah, sorry that I'm getting into really the weeds. This is like super complicated stuff, but hopefully it will pay off soon. Okay, so now this is what happens, and in fact, if we start from the Q mod Zn symmetries, we can also recover the Q mod Zm symmetries by gauging the dual Zk symmetry. Okay, good. So now what happens is that we can start from Q, and then we can get Q mod Zn by gauging some symmetry. We can start with Q mod Zn, and then gauge some symmetry to get Q mod Zn. Okay, so now let's imagine that we turn on some background gauges. So let's turn on the background gauge for Zm, and then we have a good control over its partition functions. So then that means that we also have a good control over partition functions after gauging the Zm symmetry. So we also understand what's the partition function in Q mod Zn. So in particular, what I want to do is that I also want to turn on the backgrounds for a Zk subgroup of Zn, so which I'll couple it to a background C. Okay, so this is a partition function that I will get after gauging if I turn on the background C, which is a Zk subgroup of Zn. Okay, so the next thing is that I can also start from Q mod Zn and then see what happens if we gauge the Zk symmetry. So let's split the symmetry Q mod Zn into first let's first consider the Zm part, and then also we consider Zk part. So for the Zm part, we actually also have a good control over its partition functions because there's a self-duality that relates the partition function of the theory Q and the partition function of the theory Q mod Zn. And we have a good control over the partition function of the theory Q with a Zm background turned on. So we also have a good control over the partition function of the theory Q mod Zn with a background Zm turned on. Good. So now we can turn on background gauges. So let's first turn on the background gauges for Zk subgroup. So we call it big B. And then we can also turn on the background gauge for Zm. So in particular, the background gauge of Zm will now split into a foreign form. So it's L times big B plus C. So C is essentially the part that takes care of the quotient that Zm mod Zk. Okay. So it turns out that this C is exactly the same C that couples to the Zk symmetry after we gauge the Zk symmetry. Okay, so now we have a good control over the Zm partition functions, which we know is given by the same partition functions of Q with the Zm background turned on. But potentially there's a gravitational anomaly, so we need to include this phase. Okay, so now starting from Q mod Zn, we can also gauge the Zk symmetry and get a partition function for Q mod Zm. Okay, so this is what we get. So this is so essentially what we do is that we just sum over big B, and then this becomes the partition function of Q mod Zm. So the option is that we have equalities, which comes from gauging the symmetries from both sides to obtain Q mod Zm. And also we use the fact that there's a self-duality. So now with this and the partition functions, the form of the partition function that we fixed before, and plus an additional thing is that the partition function of S2 times S2 is non-trivial. then we can prove that -1 has to be a quadratic residue of L by explicitly just computing this partition functions. And in particular, we can also show that the gravitational anomalies has to vanish on S2 times S2. So in fact, all this reasoning goes through very well on other simply connected smooth spin pool manifolds. And on those manifolds, we won't get stronger constraints, we get the same constraints, but except that we can also conclude that on those manifolds, the gravitational anomaly has to vanish. So with all this, we finally obtained the symmetry enforced gaplessness results that I stated before. So that just means that symmetry preserving topological orders exist only for very specific n, which takes the form that n can equals to k squared times L, and -1 is the quadratic residue of L. So I already mentioned that there are some conditions for -1 to be a quadratic residue of L, and now we can just plug in these conditions and then check what are the possible n's that emit duality preserving topological orders. So these are the orange numbers that I've listed here. So here we see that the minimal duality preserving topological orders exists, the minimal n that such duality preserving topological order exists is at n equals to 4. And in particular, for this black numbers, these are the numbers where duality preserving gap phases never exist. So in particular, we see that when n goes to 3, we can have a symmetry enforced gaplessness result. And also, for example, at n equals to 6 and 7 and so on. Okay, so I went through really the hard part of today's talk. I proved the theorems, and I showed that there's a symmetry enforced gaplessness. Now we can enjoy this and then start making some good use of this. So I'm going to discuss an example that is ZN lattice gauge theory. So ZN lattice gauge theory.
Let me make sure. Did I follow the notation correctly? Previous slide. L equal to 2 to the power alpha 0, Q1 alpha 1, and the next one is Q1 alpha 1. Is that repeated?
Oh, sorry, Q2 alpha 2. Q2 alpha 2. Yeah. Thank you. Yeah, that was a mistake. Yeah. And so on and so forth. Yeah. Okay, so now I'm saving really the best part of the talk at the end of the slides. Now we can actually use the theorem to say something. So let's talk about ZN lattice gauge theory. So in 3+1 ZN lattice gauge theory, it's known that there's a duality, and it's a strong weak duality. So the duality map a weak coupling theories to strong coupling theories, except that it's not a precise duality. Because when you do this mapping, you also need to couple the theory to a topological ZN2 form gauge theories. So you need to couple the ZN1 form symmetry to dynamical ZN2 form gauge theories. Okay, so this is the statements of the duality. So a direct consequence of this is that we can work at the self-dual coupling. But at the self-dual coupling, then the theory is invariant under gauging the ZN1 form symmetry, just because of this duality. And because of this, the theory has non-invertible duality symmetry. Okay, so now we can use our theorems and actually say something. So at self-dual coupling, what we can say is that for some specific n's given by these conditions, then the theory must either spontaneously break the duality symmetry or flow to a gapless phase. And let's check this with some expectations. So there are some expectations that we obtain both analytically and also from Monte Carlo. So analytically, it's very easy to understand the phase diagram at both extremely weak coupling and extremely strong coupling. So at very weak couplings, the theory just flows to a Higgs phase where there's a non-trivial ZN TQFT. At extremely strong coupling, the theory actually flows to a confining phase. So this is just a trivially gap phase with a trivial SPT. So one thing we want to understand is what happens at the self-dual coupling. So there's some results suggested by Monte Carlo. So when n is small, so for example, when n is less than 4, then it's shown that there's a first order phase transition. From numerics, there's a first order phase transition at the self-dual coupling. So what is the meaning of a first order phase transitions? It means that at the self-dual coupling, there exists 2 local vacuums. So 2 local vacuum coexist, and one of them supports a trivial, is the confining vacuum. So it's a trivially gap vacuum. The other one is the Higgs vacuum, which has a ZN TQFTs. So at this first order phase transitions, these 2 vacuums will exchange. Okay, so at this point, what happens is that the duality symmetry actually is spontaneously broken what it's doing is that it's exchanging the two vacuum. Okay, so this matches with one of the scenarios that we discussed, constraints by the duality, symmetry enforced gaplessness. So now let's ask what happens when n is larger. So it turns out that when n is larger, there are in total 3 phases that would happen as we dial the couplings. So as we increase the coupling from weak coupling to strong couplings, we'll go through 2-phase transitions. And in the middle, there's an intermediate phase, which is a gapless phase. And at this phase, the theory will flow to a gapless continuum U1 gauge theory. Or in a colloquial words, it just means that it flows to a gapless continuum Maxwell theory. And so this again matches with the symmetry enforced, the constraint from symmetry enforced gaplessness. And in fact, there's something more we can say. So remember that this point has a self-dual, has a duality symmetries. So, and the duality symmetry is preserved under RG flow. So we can use it to fix the coupling of the Maxwell theories. So the coupling of Maxwell theories is fixed to be this particular couplings, so that the theory also reproduces the duality symmetry. Okay, so so now let me move on to the other model, which are slightly more interesting. So this is
yeah. Is there anything on this slide that could not be said in the late 70s? In other words, where did you use the formalism that you built on this slide?
Where did I use the formalisms on the slides? So all these results were expected on 80s, but the things that we prove is that the theory can never flow to symmetry-preserving gap base. So in particular, the theory cannot flow to topological orders, non-trivial topological orders at this point.
That's almost guaranteed, because either there is a phase transition at G star or there isn't, right? So if there is a first order transition, this is what you said.
Correct, yeah.
And if not, it has to be self-dual. That's already clear from the lattice without mentioning the formalism.
Correct, yeah, correct. So there's one possible phases that could happen is, for example, that so there's let's say there's a Higgs phase that's weak coupling, confining phase that's strong coupling, but in the intermediate region, it's not the Maxwell theory, but for example, it can be some self-dual TQFT. That's possible, right? Just purely analytically, that's possible. But of course, intuitively, we don't expect that to happen. That's it. That's your question.
Not quite. I also don't understand why you call it Higgs.
Why I call it Higgs?
TQFT, right? The gauge group is Zn, and you see Zn, so nothing is Higgs.
Oh yeah, I call it Higgs phase. It's just yeah.
It's Higgs relative to the emergent gauge field in the middle.
Correct. But, yeah. Correct. Yeah. That's right. Yeah. But yeah, I can just call it a Zn TQFT.
Okay. So, but then I still don't see what else. It could be that this thing, the gap between them closes. Namely, there's no intermediate phase. That depends on the action.
That's true. Yeah, that's true. But I mean, do you agree that in general, just purely in general, that there's a possibility that there's an intermediate phase. It can be, for example, some self-dual TQFT, for example.
Well, it could be a first-order transition for all n. I'm almost sure that if you go look in the space of coupling constants on the lattice, you will find it.
That's right.
Intermediate phase could shrink to a point.
That's right. That's right. But what I mean is something different. What I mean is something different. That, like for example, so there's a Zn TQFT, there's a truly gap phase, but then maybe there's some phase transitions as we go from Zn TQFTs to some intermediate phase, and the intermediate phase has only one vacuum, and it's a self-dual TQFT.
Oh, I see. Okay, thank you.
Yeah, I see. Okay.
Just to clarify, I guess, Hotat, are you trying to say that you can prove the transition will be at a G star instead of having two separate transitions near G star going to an intermediate symmetry-preserving gap topological order phase? Is that the statement?
Correct. Yeah. So yeah, correct. So
there's no two separate or more transition near the G star, but I think you will say there will be a symmetry enforced gapless transition just near G star instead of a neighbor transition going to near the G star such that there's an intermediate symmetry symmetry gapped topological order phase.
Sorry, that was maybe let me just restate the statement. Maybe that would be helpful. So what I can show is that so first of all, there's a possibility there's some intermediate phase, and then there's some phase transition happening somewhere else instead of at the subdual points. And what we can show that is that this intermediate phase cannot be cannot be a TQFT that preserves the duality symmetry and also has a unique vacuum. Okay, so for the first order phase transition, indeed it's a TQFT, but it has multiple vacuum. So this is not what we forbid.
You say multiple vacuum on three sphere.
In three sphere, that's right. Multiple local vacuum.
Okay,
yeah. That's right. Yeah. I think Max has a question.
Going back to this statement, this statement is proven only for certain values of n?
Correct, yeah, correct, yeah.
But you're kind of assuming that there is some continuity in n or in this particular microscopic model, is that right?
That's correct. So the correct statement is that I can only show it for specific ends. So if I want to talk about the other ends, I'm extrapolating. Yeah. So don't trust those statements. Only trust the statement that's for specific end. Yeah.
Thank you.
Yeah. Okay. Yeah. Okay. Is there any more questions at this point? Okay. Good. So I'm going to discuss another model, which going to be more novel in two sense that there's a lack of simulations, and also because in that case we can actually make statements that's true at every end rather than a specific end. Okay, so this is a Cardy-Rabinovici model. So this model, one way to think about them is that it's a U1 lattice gauge theories, and it's coupled simultaneously to a charged electric matter and a charged magnetic matter. Okay, so let's consider this model. So one way to think about them, just to help people think about them, is that you can think about this as a U1 lattice gauge, as a U1, it's sort of a formal continuum description, is that we can think of it as a U1 gauge theories. Then we can integrate out all the matter fields. When we integrate out all the matter fields, then what we're doing is that we're inserting various Wilson and Hotat lines in the actions, and with some specific weights. And the insertion of the Wilson lines are only restricted to nth power of the fundamental Wilson lines, and the insertion of Hotat lines are not restricted. Okay, so this is a somewhat formal way to think about it in a continuum. Okay, so this model is known that there's a SL2Z duality, which is related to the SL2Z duality of a U1 gauge theory. And so what the duality does is that it maps this it's a non-trivial transformations on this complexified coupling tau. So the first generator of the duality is a T duality. So this is a duality that shifts tau by 1. So it's also equivalent to shifting theta by 2 pi. So this is a duality because if we shift theta by 2 pi, because of the Whitman effect, the Hotat line is shifted by charge and Wilson lines, and the charge and Wilson lines can be absorbed into the insertion of the other charge and Wilson lines. So this is a duality. So another duality is the S duality, which comes from the electromagnetic duality. So what it does is map tau to -1 over tau. And but when we do that, we are exchanging the electric matter with the magnetic matters. But remember that they have different charge. So then when we exchange the electric matter with the magnetic matter, we don't get back exactly the same theories. So in order to get back the theories, we need to couple it to a ZN two-form gauge theories to gauge the one-form symmetries, and then we will obtain exactly the same model as before. So this is this additional coupling to ZN two-form gauge theory is the reason why there's some non-trivial non-invertible symmetries. Okay, so the reason why I want to talk about Cardy-Rabinovici model instead of a ZN lattice gauge theory is that now I'm allowing myself to turn on the theta angles. So now, when I turn on theta angles, then I can go to a complexified couplings. which is given by e to the power pi I over 3. So this model is invariant under gauging a ZN1 from symmetry, but it's invariant under a twisted gauging of a ZN1 from symmetry rather than an ordinary gauging. So when I talk about twisted gauging, what I mean is that you can imagine that you stack this SPT on top of the theories, and then you gauge the symmetries. Okay, so it turns out that this twisted gauging also defines a non-invertible symmetries, but it defines a more novel kind of non-invertible symmetries, which we call it a non-invertible duality symmetry. Okay, so now there's another thing that happens in this theory, which doesn't happen in the lattice case theory, is that this duality symmetry actually has a mixed anomaly with gravity. And one way to think about this mixed anomaly is coming from the mixed anomaly between electromagnetic duality of the U1 gauge theory with the gravity. So what it does is that it says that the partition function before and after gauging are not exactly identical. They are identical up to gravitational counter terms. And this gravitational counter term is non-trivial on, for example, spin manifold. Okay, so there's a mixed anomaly, and we're going to use it to make statements. So let me say something about what is the expectation of Cardy-Rabinovici models from analytic sort of like estimation. So this is a very heuristic argument, by no means to be an exact proof, but this sort of gives us a rough idea of how the phases could be. So at small n, triality symmetry is spontaneously broken. So what happens is that at the triality points, there are in total 3 local vacuoles. So there's a Higgs vacuole where the electric matter condense, and then it gives us a Zn TQFT. There's a confining vacuole where the monopole condense, and then we get the trivial Zn1 from SPT. There's a third vacuum where is this oblique confinement where dion condense, and then we get a non-trivial Zn1 from SPT. So what the triality symmetry is doing is that it's exchanging these 3 local vacuoles. So symmetry is spontaneously broken. So another possibility is what happens when n is large. When n is large, I think there's a question from Maddie.
Yeah, why do you call it confinement?
Why do I call it confinement?
There's no confinement in this model.
Oh, yeah. So I call it confinement just in the colloquial sense that the magnetic monopole condense. That's all I mean. Yeah, this is the expectations from the dion free energy calculations.
But it's not. There's no confinement here. There's no Wilson loop with an area loop.
Correct. Yeah. Correct. Oh, wait. Actually, give me a second. No, actually, I think it's fair to call it a confinement because there's a Zn1 from symmetry, right? And that Zn1 from symmetry is preserved.
Does the model on the lattice?
Sorry, I said something wrong. Sorry, I said something wrong. No, I think I said something correct. There's a Zn1 from symmetry everywhere in the phase diagram.
The particles have charge n?
Yeah, so electric matters are charged n, and magnetic matter are charged
okay,
n. Yeah, that's right. Okay, good. So I have 3 vacuoles. And now the other possibility is large n. What happens when n is large? Then the theory falls to a gapless Maxwell theory. So this is somewhat similar to what we expect also in Zn lattice gauge theory. So one thing that's novel about this is that now since we turn on theta angles, then there are potentially sign problems. So a typical Monte Carlo simulation doesn't go through. And so now we really need to rely on some analytic results. So now we can use some symmetry enforced gaplessness arguments to say something rigorous. So now I'm going to talk about triality symmetry enforced gaplessness. I didn't prove in the talk, but then you can prove it in a similar kind of reasonings. So what it states is that triality preserving topological orders do not exist unless n takes the following form, unless n can be factorized into k squared times L. And then there's a solutions to this complicated equations that p times p plus 1 equals to 0 mod L. So unless these conditions are met, then the theory has then there's no triality preserving TQFTs. So the second thing we also prove, which turns out to be extremely useful in this case, is that if this TQFT exists, then it must have a trivial mixed triality and gravitational anomaly. Okay, so now using this, we can actually make some real statements now. So at the triality points, the Cardy-Rabinovici models must either spontaneously break the triality symmetry or flow to a gapless phase for some very specific ends that I listed here that satisfies these conditions. But more interestingly is that we know that there's a mixed duality and gravitational anomaly in the UV. So because there's this anomaly that exists, and then we also know that every TQFTs that respect duality symmetries and with a unique vacuums must have a trivial mixed duality and gravitational anomalies. Then we see that the theory can never flow to a duality preserving gap phase for every n. So this is the strongest statement that we can make with the anomaly. So, and another things that we can make is that if the theory flow to Maxwell theories, then we can use the duality symmetry to fix the coupling to be this very specific couplings, so that the theory has a duality symmetries. Okay, so that's everything I want to say about Cardy-Rabinovici models. So let me just wrap up. So in the talk, we discussed non-invertible duality and duality symmetry. And then we also show that this non-invertible symmetries can imply the symmetry enforced gaplessness. In particular, it means that the theory can never flow to a symmetry-preserved gap phase for some specific n. So we applied it to 3+1 Ising lattice gauge theory, and we show that a self-tail coupling, the theory must either spontaneously break the symmetry or flow to a gapless phase for some specific n. So the same thing also holds in Cardy-Rabinovici models at the duality points. And in particular, in that case, because there's a mixed duality gravitational anomaly, we can say something stronger. We can exclude symmetry-preserving gap phase for every n. Okay, so that's everything I wanted to say, and thank you for listening. Okay.
Thank you, Hotat.
Yeah, thanks.
Question, more question?
Yeah, I think Hank has a question.
Yep. So thank you for the very interesting talk. So if I remember your argument correctly, so here you're essentially you're looking at you're looking at theories that preserve the Zn symmetry, and then you're trying to exclude like being gapped, like the IR fixed point being gapped, basically. So you're classifying the duality enforced gaplessness under the assumption that you're preserving or breaking Cn, right?
No. Yeah, I think that's something I didn't emphasize in the talk. So, so here I didn't make assumptions that whether Zn is broken or not. I only make assumptions that the duality symmetry is not broken. So when I say symmetry preserving, I only refer to the ones that preserve the duality symmetries. So I'm allowing the Zn symmetry to be broken. In fact, in the example that I discussed, like for example, ZK gauge theories that are invariant under gauging and Zn symmetries. In that case, part of the Zn symmetries is actually broken. So the symmetry is broken from Zn to Zk, Zn, for example.
Right. Yeah, but my question was like how do I say this? Like the cases that you're ruling out are still associated to Zn, right? The symmetry is Zn. For example,
are you asking whether there's a Zn symmetry in the always in the theory?
Well, I mean, I can think about like S3 lattice gauge theory, right?
Yes.
But I imagine, how do I apply your thing to that case?
Oh, I see what you're saying. Okay, so
yeah.
So,
sorry, maybe I wasn't.
Yeah. So let me see whether this helps you. So so when I say the theory has a duality symmetries, I always implicitly assume there's a Zn vacuum symmetry in the theory. Okay, so that really comes in the package. And one reason why they comes in the package is that when I define the duality symmetry, one way to define them is that I want the theory to be invariant under gauging a Zn vacuum symmetry. So I already assume the existence of Zn vacuum symmetry. And in other words, when I fuse this duality defect, I also get Zn vacuum symmetries. So I cannot untangle like Zn vacuum symmetry from the duality symmetries. So as for like other symmetries, like you say, like S3 gauge theories and things like that, that I don't know. So that I don't know. Like first of all, I don't know whether there's a non-invertible symmetries, and
Yeah. I mean, the fact that you can state that for example, lattice gauge theory is invariant under duality transformation, like it's because Cn, like the dual of Cn is Cn itself.
Correct. Yeah. Correct. Yeah.
Yeah.
That's right.
But I think there are actually like more general notions of duality in this sense for non-abelian groups, like discrete groups, non-abelian discrete groups, like the quantum permutation groups and stuff, that you can actually like duality in that case, but like in that general context of duality, right? Yeah, in that context, I'm actually not sure if you say that, okay, my
by the way,
is dual, then
we should leave it at time. I think, let's see, I guess Nati has a question. Hank, are you already done?
Yeah, I'm here.
I said not Hank, question. Are you done, Hank?
Yeah.
Yeah,
Maybe-
we can chat more after the talk.
Clarify later. Let's see.
Yeah.
Maybe Nati, please go ahead.
Can you go one slide back?
Okay. Yeah. So here.
Yeah, so I'm going to ask you the same question I asked you before. How much of that could be done without the more modern technology?
Oh, good. So I would say that so what was done in the literature was heuristic estimations. So that by no means to be accurate, to be rigorous statements. That is some estimations that help us to understand, sort of like have a picture of the phase diagram. So I would say that all these results are new results, and but of course one don't need to rely on the language of calling them the non-invertible symmetries. One can derive them by just asking whether there's a TQFT that is invariant under gauging already.
But I thought the reasoning in their paper, if I remember correctly, was very similar to the reasoning here, namely, there are various duality transformations you can perform, and that maps various regions in the parameter space. And if you're at the fixed point of this map, you know that something has to be there.
Oh, okay, good. Yeah. So what they did was was something like this. So we understand very well at asymptotic regions. So for example, at weak coupling, we know it's a Higgs vacuum. Okay, so then using SL2Z duality, you can map it to various different regions, but then you can only map it to regions. So it's hard to make actual statements at the boundaries of the regions. So you know roughly some regions has to be in some phases, but it's hard to make actual statement at the triality points, for example, where various regions could meet. Does that make sense?
Maybe I'm just too old-fashioned, but when I read that paper long before you were born,
yes.
Reasoning I thought was the following. People did similar things in 1+1 dimensions. There was a ZN clock model in 1+1 dimensions, and you can dualize it and find that depending on n, it has 2 phases or 3 phases, etc., etc. And there's a self-dual point, etc., etc. All these things generalize what we know about Ising. And I thought that paper, there's actually 2 papers, did the same thing in 3+1 dimensions, but the logic was exactly the same. And what you did here was very nice, and it makes it much more precise, but I'm trying to see whether the more powerful formalism leads to new results or only makes the old results more rigorous.
Oh, okay, good. So the way I will characterize the old result is that it's suggestions of the phase diagram. It's not a proof of the phase diagram that something like this happens. Because what they did was estimations of free energies, and then they sort of estimates what could possibly condense. So it's suggestions. And what we did here is rigorous statements using like all this technology, and our rigorous statements sort of confirm or matches with the expectations. Yeah.
I see. Thank you.
Yeah.
And by the way, great talk. I enjoyed it.
Yeah,
and
thanks.
my students doing well.
Yeah, thanks. Is there any other questions?
So I think we should thank Hotat first. Thank you, Hotat.
Okay, thanks everyone for staying. It's really Yeah, I didn't expect to be such long.